Great. Welcome, everyone, and welcome to the new colloquium of the series. We're very excited to welcome Melissa Lindell from Harvard University, who's going to talk about efficient OCR for building a diverse digital history. Professor Dell is a professor of economics at Harvard University, and prior to that, she was a junior fellow at the Harvard Society of Fellows. She's received several awards for her work, the most recent one being the 2020 John Bates Clark Medal, awarded each year to an American economist under the age of 40 who is just to have made the most significant contribution to economic thought and knowledge. Melissa's research focuses on economic growth and political economy. She's also examined factors leading to the persistence of poverty and prosperity in the long run, the effects of trade-induced job loss on crime, impacts of US foreign interventions, among many other topics. She has also developed deep learning-powered methods for curating social science data at scale, which are released in several open source packages. And this is the kind of work that supports many of her current projects, which rely on digitizing historical sources that are far too large for manual digitization, hence the project that she will be presenting today as well. So welcome, Melissa, and I'll let you take it from here.
All right, great. Thanks so much for the invitation. Thank you, everyone, for coming. I'm going to be talking today about efficient OCR for building a diverse digital history. This is joint work with Jake Carlson, who's a graduate student here at Harvard and a former pre-doc, and Tom Bryant, who is a pre-doc in my lab. And so digital texts are central to the study, dissemination, and preservation of human knowledge. Tens of millions of users consult digital archives on a daily basis in Europe alone, yet many billions of documents remain trapped in hard copy in libraries and archives around the world. So for instance, the US National Archives has about 14 billion page scans of documents. The National Diet Library of Japan has something like 5 billion document scans. There's just a massive amount of information. And these documents are very diverse in terms of the character sets that they use, their languages, fonts or handwriting, the printing technologies employed, and various artifacts from scanning and aging. Having digital text is extremely important in a variety of ways. It makes it possible to have automated indexing and search of documents so that you're able to find what you're looking for without spending mass amounts of time in a dusty archive somewhere. It's necessary to do computational analyses, to do statistical analyses, to train large language models on historical public domain texts. And in general, it makes for easier consumption by both researchers and the public. So in order to be able to digitize on a massive scale information that's trained in hard copy, we need optical character recognition, or OCR, that's highly extensible to these very diverse types of documents, languages, etc., that's accurate. Especially if we're doing things like statistical analyses. If you have too high of an error rate, it won't be useful information. And it also needs to be very cheap to deploy, because there's billions of pages of documents out there that we would like to digitize. And so current OCR technology falls short of these goals. Poor performance is widespread, especially outside very high resource languages like English. And so this has spurred a large post-OCR error correction literature, although there's only so much you can do if sufficient information is destroyed to be able to reconstruct it after the fact. It's also skewed digital history towards a limited number of settings that are not representative of the diversity of documentary history. So historians spend a lot of time thinking about how people who leave behind documents are not representative of humanity, and that's very true. But when you take that additional step from documents that exist to documents that are in high quality digital format, that significantly skews the sample even further, very heavily towards the US, a few settings like the UK and Germany, where there's been a lot of resources put into digitization, where you have huge parts of the world where documents do exist, but very little has been done to digitize them. So just to give an example of how poor current technology can be, we wanted to digitize firm level records from Japan in the 1950s. They're printed. They're not that old in the scheme of documents that people work with, so it seems like there's nothing too crazy here. And yet the best performing OCR, which is from Baidu, gets over half of characters wrong, which is just completely useless for anything you'd like to do with the documents. And when we tried to dig into this and understand why OCR is performing so poorly, when you go to even a slightly lower resource setting, what we really discovered is that the predominant architecture used for OCR was not designed with the objective of digitizing the world's knowledge. You know, OCR is by and large a commercial technology. It's more designed to be complicated for your competitors to imitate. And because of this architecture, it makes kind of the predominant OCR architecture very difficult to extend to lower resource settings, whether it be a lower resource language or historical documents in a high resource language. And so, in short, OCR is typically modeled as a sequence-to-sequence problem, in where you take learned embeddings from a vision model, and then you decode those into text using a learned language model. And so you have both a vision encoder and a language decoder in that. You know, if you wanted to do that with modern technology, that would be a seek-to-seek transformer model. And the problem with sequence-to-sequence models is they're incredibly data and compute intensive to train. In order to train a vision language model, you need a vast collection of labeled image text pairs and significant compute. You know, even having a pre-trained language transformer doesn't help you too much, because the language model in an OCR is taking these vision embeddings as inputs, not tokenized text. So even for high resource languages like English, it's costly to train or tune open source seek-to-seek alternatives. If you're working in a low resource language, you know, where NLP resources are minimal to start with, it's probably not going to be feasible to even use this architecture. And so we tried to go back to the drawing board and rethink how OCR is done. And we developed a novel open source architecture called Efficient OCR, or FOCR for short, which is designed for researchers and archives who are seeking a very sample efficient, meaning it learns efficiently from minimal data, customizable and scalable OCR solution for diverse documents. And we try to combine the simplicity of how OCR systems were first conceptualized 100 years ago with deep learning to really bring OCR back to its roots, which is the optical recognition of characters. FOCR is central to a broader suite of digitization tools that we are developing. So we have an open source package for recognizing document layouts. FOCR, we have an open source package to accompany it. We have open source packages for record linkage, and also other open source programs for other tasks that we're working with in NLP. All right, so now I want to delve now into OCR architectures and how by innovating the architecture, we're able to have an OCR that's much more extensible to lower resource settings. So modern OCR is going to overwhelmingly use a neural network. It could be a convolutional neural network or a vision transformer to encode images of lines of text into semantically rich vector representations. So you take a line of text, divide it into arbitrary patches, and embed those as vector representations. And then these vector representations need to be decoded back into the associated text. And so traditional seek-to-seek OCR architectures typically will require text line level inputs, and they do not localize individual characters. Rather, images or their representations are divided into fixed size patches. And so essentially think of taking a sliding window and moving it across a line of text. And so the first place that FOCR is going to depart is that we're going to localize individual characters or words, depending on the language, and whether it's a character or word-based, using modern object detection methods. Okay, so you can see here on the bottom line, seek-to-seek, it's not detecting the individual Japanese characters in those lines of text, whereas the first thing that we're going to do is to detect the coordinates of individual characters. Okay, so seek-to-seek, once it has encoded these patches of the text line image, it's going to use a learned language model to decode those back into text. In contrast, FOCR is going to learn meaningful representations of the individual localized character crop or word crop images. So crops of the same character or word, regardless of the style they use, the font they use, any noise in the image, are mapped to vectors with a high cosine similarity, and crops of different characters are mapped to vectors with a low similarity. And these representations are then going to be decoded in parallel by retrieving their nearest neighbor from an offline index of character or word image representations that are created from a digital font. And so you can see that here on the top line. So first of all, we are localizing those individual characters. And then we have the character recognizer, which is an image encoder. It can be a CNN or a vision transformer. And we feed those individual crops into it to get vector representations of them. And then we have this offline embedding index where we just take a digital font and embed every character in it. And we figure out what character this vector representation corresponds to by computing its nearest neighbor in this index created from a digital font. And so there's no learned parameters in this decoding. Once we have a good vector representation of the character, we just need to compute the nearest character in this index, right? Whereas with traditional seek-to-seek, you're learning an entire language model here that's used to decode these representations. And that is enormously costly. It's costly to run because you have to do sequential decoding. You can't do it in parallel. And it's particularly costly to train, at least if you want to use modern architectures like the transformer. All right. So for alphabet scripts, words are going to be the logical unit. Of course, it's not possible to create a fully comprehensive word index. Words can be hyphenated at the ends of lines. There's lots of proper nouns or antiquated terms that might show up. And so what we do is to recognize words, and if the words are within a cosine similarity threshold, their representations are within a cosine similarity threshold to the nearest neighbor in our word embedding index, we digitize it as that word. But if they're below that cosine similarity threshold, we default to character level recognition. And in practice, this works really well. And so if the word can be identified in the offline index, it is. But if it's too dissimilar, we just default to character recognition and recognize the individual characters. And this allows us to deal with things like proper nouns or words that get hyphenated at the ends of lines. All right. So within FOCR, we can use different vision encoders interchangeably, both to localize the characters and to recognize them. And so in the paper, we consider three main state-of-the-art encoders. So a transformer model, a convolutional model, and a small convolutional model, which uses lightweight architectures that are designed for mobile phones. And so specifically, the base convolutional architecture is ComNext. This is a ComNet for the 2020s. In practice, it's kind of state-of-the-art on a variety of tasks, which is why we choose it. We use a transformer model, Excite, for the localizer and the recognizer. And then for the small model, we use YOLO for object detection. This is a one-stage object detection framework, which is very fast to run. And then we use MobileNet small for the recognizer. This is meant to run on mobile phones, and so the advantage is it's extremely, extremely cheap. We also look at other vision transformers like SWIN and VIT base. Why did we choose these? Well, ComNext is the state-of-the-art CNN. Excite has the comparative advantage in modeling fine-grained features that you often see in characters because it's able to accommodate smaller patch size through a linear complexity attention mechanism. And then the lightweight model we chose because it's been super optimized to run very quickly on a low-powered machine. In the first stage, as I mentioned, we're going to use single stage for the light model because it's super fast, and then Cascade CNN or Detectron 2, which are other kind of two-stage object detection frameworks for localization in the base models. All right. So creating quality annotations by hand is costly. Like if you want to make an undergraduate think they should never be an RA and never want to be an academic, ask them to digitize documents for training OCR, right? People don't like to do this. And so we're mostly going to train this on digital fonts. We use 43 different digital fonts, and in these different digital fonts, different characters or the same characters are represented in different ways, right? So we get different views of the same character by using digital fonts. We're going to add some image level transformations to them, just standard image transformations like, Gaussian blurring, grayscale, etc. We're going to pad the words to make the image square while preserving the aspect ratio. This is actually quite important in OCR, right? Because these vision models, they almost always take a square input. And if you just resize using centering, it will really distort the aspect ratio of the character. The model learns from hard negatives. And so kind of a general fact of contrastive learning, which is the way we're going to train this, is you need to give the model hard examples of negative pairs, because otherwise it's just not going to learn, or it's going to learn very slowly. And so we're just going to mine those. We're going to take a first pass at training the model with just the positive pairs, so different representations of the character from different digital fonts, and random negative pairs. Then we're going to use that to figure out what characters using this initially trained model are most visually similar to the query character, and we're going to use that to form negative pairs, so that the model has these hard examples to learn from. We use a supervised contrastive loss function, which allows you within your batch to have multiple positive and negative pairs, which is kind of informative in this case because we can have multiple positive pairs with digital fonts, and then we have multiple negative hard pairs via these different hard negative groupings. And so the basic idea is that you're incentivizing the model to give the same representation to different views of the same character or word, and different representations, above some threshold distance to different characters or words. All right, and so it's essentially it's a straightforward application of contrastive learning in the image space. No language model at all. We're just learning to visually recognize characters by training a model to map character crops to vector space such that if it's the same character, it gets a similar representation. If it's a different character, it gets different representations. Words work the same way as characters. All right, so evaluating how we do is going to require benchmark data sets that are representative of the diversity of documentary history. And traditional OCR benchmarks focus on commercial applications, primarily on receipts. And that's really what drives most of this literature, is digitizing receipts. You go out to dinner, you need to get reimbursed. That's a big part of the commercial OCR market. We spend a lot of time looking at kind of every benchmark under the sun that exists. And, by and large, they are not focused on low resource settings. And so we build novel data sets. And so first of all, we're going to draw on documents from historical Japan. We are motivated to do this by social science questions. Japan experienced this incredibly rapid transformation from a poor agrarian economy to a wealthy industrialized nation in the 20th century. This is not as well understood as it could be, in part because all this data that exists has never been digitized. We have horizontally and vertically written tabular data. So this is common in Asian languages. You can write things horizontally or vertically, and you have important documents with both of those orientations. They provide rich information on firms and personnel. We also have a 1930s prose publication that provides detailed biographies of tens of thousands of individuals. And these texts could contain over 13,000 kanji characters, most of which are no longer in use. And that's part of why it's enormously costly to digitize these, because there's so many similar looking characters, and a modern Japanese speaker will actually have a hard time distinguishing them. The second context is the Library of Congress's Chronicling America collection. This contains around 20 million historical newspaper page scans. Library of Congress provides an OCR transcription, but the quality is very low. It reads the newspaper like it's a single column book, even though there's multiple columns. It doesn't distinguish headlines from articles, from captions and advertisements, and it's full of OCR errors. And so we choose to focus on this, first of all, because it helps inform how FOCR performs even in the highest possible resource setting, which is English. And also these results, because they're just using like the visual appearance of characters and words. They're not using a language model. So it's extensible across, any language that uses the Latin script, which is about 2/3 of endangered languages. And then finally, Latin and kanji, Japanese characters, just have very different aspect ratios and complexity. And so it's a good way to examine how this framework is going to do again on very different types of characters. And so this is an example of what these documents look like. You can see that the Japanese can be written vertically or horizontally. You see the newspaper columns there. Newspaper columns tend to be very kind of narrow with multiple columns on a page. This is our training and evaluation data. These are pretty minimal. So you're looking at characters in the thousands, which is something you could probably label in an hour. And so this is mostly using digital fonts, which is minimal training on target data. We also create a second benchmark data set for the newspapers, where we take one randomly sampled day per decade from the 1860s to the 1920s. And that makes this a really hard set because most of the content comes from later in the period where it's easier. But this is showing us across the period, in general, where we're evenly weighting each decade, even though in reality, the later content is much larger. How well are we doing? And you can see here that this is they're newspapers, but it's a really, really diverse data set. You get kind of all sorts of kind of noise, et cetera, in them. We are also interested in measuring zero-shot performance, so how well we do on a data set where the model hasn't seen anything like it in training. So we just hand digitized a randomly selected sample of text lines from the U.S. National Archives. So we just pulled out documents at random, digitized them, and then we'll evaluate how we do on this. And you can see typical features of archival data here, like somebody's written on top of the print with a pencil, which is something our model didn't see in training, but you can see there from the OCR that it's not perfect, but it's able to get the gist of it. Finally, we use an existing data set to train and evaluate a model on polytonic Greek. We do this in part to provide a demo notebook. You can use it to train your own polytonic Greek model on Google Colab, for free or for kind of the minimum plan. So it trains very cheaply. And this model kind of on this set of documents will outperform Google Cloud Vision. Okay. So we haven't done handwriting at this time, just because of, mostly because of resource constraints. So there are handwriting benchmarks like IAM. But when you look at these as an economic historian, you realize these benchmarks are just way too easy. I could take the benchmark and train on it and do well, but that wouldn't mean that it would work on kind of the handwriting that economists would typically see in historical data sets. And so if you wanted to train FOCR for handwriting, at least in resources like English, where there are high quality synthetic handwriting generators, you would use these synthetic handwriting generators to generate synthetic handwriting in different styles and use that handwriting in the same way that we use digital fonts. So you're mostly not having to label by hand. And so I think this could be done. We just haven't had the bandwidth to do it. All right. So we're going to measure the accuracy of OCR using the character error rate, which is just the Levisham distance between the OCR string and the ground truth, normalized by the length of the ground truth. And so if you have a character error rate of 5% or 50%, that means you've gotten approximately half of the characters wrong. We're going to make a set of different comparisons. So we'll compare to off-the-shelf models, Google Cloud Vision, Baidu OCR, and Tesseract. You can tune Tesseract, but most people, that's only a recent ability, and most people don't use it that way. And so the reason we compare to these off-the-shelf OCR models is because this is what people overwhelmingly use in practice. And so this answers the practical question of how does FOCR do relative to the models that most people use. But we're also going to fine-tune or train from scratch open source models, Easy OCR, which is a convolutional recurrent neural network, so based on older technology, Microsoft's Transformer OCR, which is a sequence-to-sequence encoder-decoder transformer model for OCR, and paddle OCR, which, like FOCR, abandons the language model and just uses vision, but does so sort of in a more complicated way that doesn't recognize characters. And so we can train these from scratch on the same data that we train FOCR, and it gives us a more apples to apples comparison. Okay. So in addition to kind of training those from scratch, we also fine tune them. So in the case of transformer OCR, it was trained on 684 million English synthetic text lines. So huge amounts of resources went into training this, right? And so if you want to use this, you might say, is it better for me to take FOCR and train it from scratch, or to fine tune on the same data, TROCR or EasyOCR? So we make that comparison. And then we do this from scratch comparison for apples to apples comparison between these architectures when it's supported. And so these are the base results you can see on the horizontal and vertical Japanese tables. We have a character error rate of well under 1%. And so the OCR is on these very difficult documents is looking nearly perfect. And you'll see on the next slides, the next best thing on the vertical Japanese is getting over half of the characters wrong. We also do pretty good and better than anything else on the Japanese prose. The error rate's a bit higher because in some places the documents are illegible. And we do reasonably well on chronicling America. So on the random sample, we get about 1.5% of characters wrong, a bit worse on the day per decade sample, since that's skewed towards the very early period where the documents can be very difficult to read. Okay, when you look at what FOCR gets wrong, so this is character recognition, it's confusing things that look very, very similar to each other. And the same thing in Japanese. I mean, with some of these characters, you almost have to stop and squint and say, wait a minute, how are these different? And so the one in green is the prediction and the first one is the correct one. And so you can see it's confusing things that look really quite similar. When we compare to alternatives, nothing's doing very good on the Japanese. Generally Baidu OCR is doing the best, but not doing well, not even necessarily usable in a lot of it. In contrast, on the newspapers, Google Cloud Vision does very well, but I'll tell you there's a catch, which is that it would be very, very expensive, and I'll go over those numbers in a minute. When we look at other alternatives, when we fine-tune other alternatives, you're still kind of better off training FOCR from scratch by and large than fine-tuning the other alternatives. The only exception is the transformer OCR. By Microsoft, which is the transformer seek-to-seek model, and that does pretty similar fine-tuning it to training FOCR from scratch. And so this is performing very well relative to these other architectures that you might choose to use. So Google Cloud Vision, it does very well in these tables, but the catch is that Google Cloud Vision is not able to recognize the layouts of these newspapers. And so if you wanted to do that well, you feed it one line at a time, which is what this test does. It doesn't do that well when fed full scans or even when fed articles, because it gets confused about the layouts. And the problem is that it charges per image, which would imply a cost at current prices of 23 million US dollars to digitize the Library of Congress newspaper collection at the line level. Whereas I had $60,000 to digitize those records. So obviously falling way short of 23 million. As I mentioned on the English, the Transformer OCR by Microsoft is also comparable. It has almost the same character error rate, maybe very slightly lower if you fine tune it. But FOCR runs 48 times faster. And again, that means it's 48 times cheaper. So if I had to pay, 50 times 60,000, that is still, not anywhere near to my budget, right? And it's just, it's dramatically faster, right? Because you can, because you've gotten rid of the sequence-to-sequence component, you can parallelize inference across characters or words. Whereas if you're doing seek-to-seek, you have to do auto-regressive decoding, right? Because you're predicting what comes next. On English, actually, the most plausible alternative that's scalable is fine-tuned EasyOCR, so fine-tuned on the same data that we trained FOCR on. this is an older model. It only has 3 million parameters. It's based on older technologies, and it's just significantly less accurate. For horizontal Japanese, the next best alternative is paddle OCR, but FOCR is 3 times more accurate. For the vertical Japanese, there's just nothing else that is even usable. Like, this is a sufficiently low resource setting, even though you don't necessarily think of Japanese as being a really low resource language, but in the world of OCR, if it's vertically written, it is. And there's just not even anything else that produces a usable output. This is just showing you the lines processed per second, and you can see that the FOCR small model is quite fast. All right. So you might be wondering, well, you did tune, granted it was as many labels as were created in an hour, but you did tune on the target documents. How would this do on something that it had never seen anything like it in training? So we take our model that's only trained on the newspapers, and we see how it does on randomly selected documents from the US National Archives, which is, I think, about the most difficult sample that you're going to find in like typewritten English. And it's pretty much on par with other OCR technologies. For whatever reason, TR-OCR actually does really bad. Google Cloud Vision does somewhat better, but again, you have the problem that that's with line level inputs and it's expensive. So we think that these results could be significantly improved by including a random sample of documents from the National Archives in training. And, at some point we'd like to be able to crowdsource that effort. Since again, I think if I ask an RA to label those, even if it only takes them 2 hours, they might decide they don't want to be an RA anymore. All right. So I want to now to quantify sample efficiency. So we've taken a really minimal amount of training data and it's really doing well. But what we're going to do to quantify that is we're going to take our architecture, this image retrieval architecture that FOCR is based on, and then we're going to take the other open source models. So Transformer OCR only supports English, but we can do it for English. And then the convolutional recurrent neural network, the older technology from Easy OCR, and Paddle OCR, which is this other vision-only model, but that doesn't recognize individual characters. We're going to see how well they do trained on different splits of our training data. And so honest view is 99 labeled table cells. And so like a very tiny amount of labels for Japanese and just 21 rows from newspapers, and the rows are short because the newspapers have columns. FOCR's character error rate is only 5% for the Japanese and 7% for the English. And so it's basically learning what it needs to learn from digital fonts, and it only takes really, really minimal amount of target data to do well. And so on the left is for the English newspapers, and you can see at the top, that's Transformer OCR base and small. It's not learning anything from this amount of training data, and that makes sense. Like Microsoft trained it on 670 million text lines for a reason. It's just insanely costly to learn a Transformer seek-to-seek model. And you can see in general that FOCR is training well. Okay, so I just wanted to make a quick aside about embedding models, which is what this essentially is, right? So we're taking digital fonts and we're learning how to map a character crop to a vector space such that the same character is nearby, even when it's written in different ways and different characters are further apart. And so you can use kind of this method much more generally. And we've used this across a bunch of different applications in our lab, not just for OCR, but for nearly everything that we've done. And essentially what we're able to show, if you just take an off-the-shelf model and use its representations, that tends not to work very well. There's a lot of information in an embedding. And also the geometry of the space is not very desirable. But you can fix that very efficiently through contrastive training. And so in general, contrastively trained embedding models learn a mapping from some type of unstructured data like images or text to a continuous vector space such that instances that belong to the same class have similar vector representations, and instances that belong to different classes have dissimilar representations, which we call embeddings. And so these embeddings can be used for nearest neighbor retrieval, which is what we do for FOCR, right? We take a crop of the letter C, we map it to embedding space, and then we retrieve its nearest neighbor to figure out what letter that is. They can also be clustered to group instances together. And so unlike with classifiers, you don't need to know the number of classes ex ante. There can be a very large number of classes, and new classes can be added at inference time, which we do all the time with OCR. There's a new character in a set of documents we want to OCR. We didn't include it in training, but we can just put it in there at inference time. You can't do that with sequence to sequence. And so we just kind of did a fun exercise on this with the comparative agenda. So now we're in the world of text data sets. This is congressional legislation. We want to map the legislation to a vector representation such that bills from the same topic category are nearby, and bills from different topic categories are further apart. If you take a model off the shelf, doesn't do great. You train on a modest amount of data, it does really good. So this is plotting the cosine similarity between embeddings of legislative text within topics in the blue and across topics in red. So you can see that once you've tuned a little bit, you're doing a really good job of separating out embeddings such that things that are the same topic are nearby, things that are the different topic are further apart. It applies well to legislation from the UK, even though I never saw it in training. And this is just showing that the model converges very quickly. And so all to say, we found in general that this technique that we employed in efficient OCR, where you contrastively train a neural network to map text or images to vector representations, such that representations of things in the same class, like the same character, the same topic, etc., are nearby, and different classes are further apart. This very efficiently helps us to perform well on really diverse problems. So for example, we detected which newspaper articles came from the same underlying newswire in the presence of considerable noise and editing. We detected which images came from the same photo wire, even though the quality of these varied vastly and they were heavily cropped, etc. We detected what the biggest news stories were in each year, again, by doing contrastive training, map the same story to similar representations, different stories to different representations. We had no idea what the stories were ex ante, and it was a way to explore the data. We have a tool called News Deja Vu, where you can take a modern news article, mask out the named entities, and retrieve the most similar historical article. And again, it tends to work pretty well. We've used this approach to link records together, to disambiguate entities to Wikipedia and the US Census. And so in short, there's like lots of different applications of this method, not just to OCR, but to tons of different problems with text and images. And it tends to be very sample efficient, which is good because we have minimal labeling capacity. All right, so we've taken FOCR, going back to FOCR, we've taken it and we've used it to liberate data at scale. So we've digitized and released 20 million page scans in Library of Congress's Chronicling America collection. We're digitizing more data as we speak from off-copyright newspapers. And so what we're going to do is, first of all, use a layout model to detect the newspaper layout. So what's a headline, what's an article, what's a caption? We're going to remove illegible content because you don't want to think you have something in the database when you don't, because it's illegible. Then we use efficient OCR to digitize the text, and finally we'll associate headlines with articles. So this is what the layouts look like. Along with this, we released an open source package called Layout Parser that uses deep learning to recognize document layouts. And we aim to make it easier for people to use deep learning pipelines in their own document layout tasks. And I have a lot of students who are using or have used this package. We developed active learning methods to reduce labeling requirements as well, which I won't go into detail, but are helpful. The data set, the American Stories data set, contains 1.14 billion content regions, including over 438 million articles. You can download it on Hugging Face. We have tutorials. A big team of people worked on this. So that's data set statistics. So the Library of Congress had an OCR that was very poor quality. You can see here that our non-word rate is shifted significantly to the left. And when you look at sort of actual tasks, I know I'm going through this quickly, but just like take it on faith that we do various real world tasks, topic classification, detecting reproduced content, you do much better with our OCR. We also have a data set called headlines. This is for a later period, 1920 through the 1970s. And we use a deep learning model to figure out which articles came from the same newswire source. And over half of content in these newspapers, local newspapers, came from a newswire like the Associated Press, but the local papers wrote their own headlines. And so we can use this to create a semantic similarity data set that's like different ways of saying the same thing. And there's over 400 million pairs in this data set. We also use it on the Japanese data. Our goal is to build a knowledge graph of the Japanese economy that contains things like shareholding patterns, family ownership, financing patterns, board of director networks, occupational histories, family connections, spatial locations, supply chains, etc. All of this information is in these historical firm and individual level records. We needed this really accurate OCR to do this because Japanese individual and firm names are often only a few characters long. If you get a single OCR error, it can create significant information bottleneck and make it very difficult to link the records. And so we start out with hundreds of thousands of pages that look like this. We recognize their layouts with Layout Parser, just like with the newspapers. We OCR them with FOCR. We have an additional step where we need to link firms and people together across publications. People would traditionally use an edit distance metric like this, just say how many edits do I need to make to turn one string into another, or how many n-grams do they have in common. This is, difficult because there can be different ways to say the same firm name, right? We developed a package called Link Transformer, which uses large language models for record linkage and other data manipulation tasks. Again, this is contrastively trained, so it's the same architecture under the hood as FOCR, but now we're working with text data. And you can use any model on Hugging Face with it, any OpenAI embedding model. We've also trained our own collection of over 20 open source language models for 6 different languages, as well as a multilingual model to perform different record linkage tasks. And so it's straightforward to use. One of my favorite applications is you can use it for multimodal linkage, which is something I've wanted to do in a lot of comparative projects. And I had to abandon the projects because it was too difficult to homogenize things like product categories or firm names across multiple languages. But a multilingual language model can handle this with ease. Again, using the same idea, you map firms or products that are in the same category to similar representations, just different categories to different representations, and then you retrieve the nearest neighbor. And we make it easy to train and share your models. You can also combine linking with the image crops and linking with the text. So I won't go into detail, but we have a multimodal model for this. And this is how we ultimately create this knowledge graph of the Japanese economy. And so this is a snapshot of it. This is supply chain networks from the 1950s. Japan was dominated by large firms going into World War II. The US blamed those firms for the militarization of Japan, came in after World War II, tried to break them up through antitrust and other measures. Then the US left in 1953. What you can see is in 1956, the most central firms in Japanese supply chain networks, and so the biggest dots in this picture are all the big firms that the US tried to break up. And so in short, when the US left, the economy kind of went back, and it's kind of mind-blowing. I mean, these were the biggest firms pre-war. Japan, a big part of Japan is burned to the ground. It's occupied by the Allies. It's about the biggest shock you can imagine, and yet kind of when the dust settles, it's the same big firms that continue to dominate the economy, despite kind of every effort to break them up. All right. So we can do various extensions to this. So in FOCR, we're saying we have a representation for this character. What's the nearest representation in this offline index to figure out what the character is? But you could also just say, what's the similarity between two characters in this embedding space? And so, people have long appreciated in record linkage that not all string substitutions are equally probable. People have hand engineered lists to take account for that so that characters that look similar or names that sound similar have a lower substitution cost when you're trying to link records together against sources. But the problem with this is it's not extensible to low resource settings because these lists have been created by hand. And again, they mostly exist for higher resource settings. So what we can do is just kind of take different versions of the same character in different fonts, right? Essentially just like we do for FOCR. So this is an example for Japanese, Korean, traditional and simplified Chinese. These are ways that the same character can be rendered in different fonts. We train just like we did for FOCR. So if it's the same character, give it a similar representation. If it's a different character, give it a different representation with supervised contrastive loss. And then we look at the similarity across different characters now. And what you can see is we have an example character, and then we have its 5 nearest neighbors in this vector space that the model creates. And you can see that characters with a similar visual appearance are located nearby. And so what we do is to just take the distance between the pairwise distance between any set of characters in this space. And that is the substitution cost when we link records and we show on real world data and on synthetic data OCR with different OCR engines that across OCR architectures, OCR confuses characters that have similar visual similarity. And so if you take this into account when you're linking records, you can significantly improve record linkage just using the visual appearance of the characters. And so there's an OCR error. You can figure out what record, what firm that should be linked with by accounting for the fact that the OCR error probably confuses visually similar characters. And we actually showed that you can extend this to ancient Chinese. So these were characters from over 3,000 years ago. And again, we have like a query character, and then we say, what's the nearest character? Kind of, you see the ancient Chinese character, a modern character that descends from it, which doesn't necessarily have the same meaning, but descended from the ancient character. And then you see a translation of the meaning. And what you can see is that in ancient Chinese, visually similar characters can denote related abstract concepts that have been recognized in the archaeological literature. So law and learning are similar to writing. Different types of government officials have similar characters. History is related to things like conquest and government official. And so you can see kind of that just by using a vision transformer to quantify the visual similarity of characters, it is informative to how kind of ancient peoples thought about the world. And then this is also just an incredibly low resource setting, right? There's obviously no transformer large language model for ancient Chinese, but just using the visual appearance of characters, we could recognize them or compute their similarity. Okay, so just in short, in designing this package, it was really important for us to have community engagement. If we want to extend documentary history to low resource settings, we need to engage researchers with knowledge of those settings. And for that reason, we wanted to make an OCR that's both very extensible. We wanted it to be very cheap to train. So Transformer OCR by Microsoft was trained on 32 gigabyte V100 cards, which is a multi-million-dollar setup only Microsoft can afford. We were able to train the small FOCR model for free with student compute credits on Google Colab. And so the training's kind of minimal. We have a user-friendly package to try to make it friendly for researchers to use because we really want to engage the open source research community in this. We do that by focusing on characters and words. By making it extensible to different languages, by getting rid of the language model. And so first of all, focusing on only characters or words makes it a really parsimonious problem because then you just need to recognize the visual appearance. It also makes it easier to label. Annotators can select which character or word annotation is the most similar, which one is correct. using an app. All right. By getting rid of the language model, we can extend it to low resource settings. It becomes much more broadly applicable. Characters don't need to be seen in sequence during training, so you could add new characters at inference time. It also makes it easier to mix and match scripts, which is necessary for some low resource languages. And you can expose it in training to whatever distribution of characters you want, which isn't the case with multilingual seek-to-seek training, right? So English has a certain mix of Latin characters. Cherokee would have a different mix, right? And so if you wanted to OCR Cherokee, you could expose it to that different mix and training, whereas if you were trying to do multilingual training, most of your training data would be on English, so it wouldn't work well for an endangered language using the Latin script. We separate localizing the characters from recognizing them, which may be theoretically desirable and also practically minimizes the need for training data and makes it easier to sub in new neural networks as the literature advances. As I said, we have an open source package, and it achieves fast CPU inference, so can be scaled cheaply to lots of documents, which again, we hope will engage the community. Of course, there's shortcomings. In principle, sequence to sequence by using the context should help you to do better. We found in practice, with the exception of Google Cloud Vision on English, that that's not really the case. Probably because it's just kind of so costly to learn a transformer seek-to-seek model that only for these super high resource commercial settings has anybody done it. Of course, if your document is illegible, language can help provide educated guesses. You might have a hard time finding anything that works if the document is illegible, but obviously a vision-only model won't work if the document is illegible. And in the future, we'd also like to train on a broader diversity of documents to improve zero-shot performance and incorporate handwriting. All right, so in short, massive quantities of highly diverse documents are trapped in hard copy. Digitizing them requires an OCR that's simple and cheap to customize and deploy to these very diverse settings. And so we designed FOCR with these objectives in mind, and we hope that it will encourage further community engagement with OCR and make it easier for researchers to study a diversity of different historical settings.